it's a new spot for you too.
Yeah.
It's wild. Yeah, it's wild. Just a quick, I just want to put up the definition here. This pen blows. It's better. I almost thought you had a collared shirt on. Oh, you do?
Well, it's like
It's
got a
kind
little.
yeah, it's good.
Yeah.
It's good.
I haven't busted out my polos yet this year, actually.
Oh, wow.
I got a couple during firm.
Yes, this is good. Thank you for the reminder. Does anybody have corrections
Oh, yeah.
today? Yes. Thank you for the reminder for all of us. Thank you.
Thank
you. What's that? Oh, yeah.
Yeah.
And you don't need them anyway.
Okay.
Fine.
You sure?
And you got the extra credit. I just have to record it. Like you got over 100%.
Okay.
Is that unsatisfactory? You want the ultimate over? It could be better. It could be better, man. You could have not missed that 1 point.
Yeah, thank you.
Yeah, you're welcome. Oh, thank you. Oh, thanks. No, good, cool.
It's because the first
You
problem,
did.
but you did
You
that.
wrote the form down. Yeah, sorry.
You actually did it.
Okay.
Yeah, you're the only one who like, was it?
I don't know.
No is one.
No, I asked if it was right. Like.
Oh.
you
Oh, I
remember?
haven't looked at it
Oh.
yet. So,
You'll
yeah.
have to look at
And
it.
if you need, like, if this is up, if this, I should have given it back to you, but I didn't think you would be doing corrections. So if you need, we'll talk. If this is upsetting in any way.
No.
Okay,
It's
all right.
That's fine.
Okay,
Yeah,
cool.
thank you. My bad.
Good, well, my bad too. Whoa, what's going on here? I'm coming apart. Anybody help us on number 1? What's the answer? I gotta sit like this with my head to the side so this thing doesn't fall off.
Can I throw out a random answer?
What's that?
Can I throw out a random
I would love it.
What if it's infinity?
That's a great answer. Not just random, but great. Yeah. How did you deduce that?
I just did the integral one and then that'd be like x, right? And then just plug in infinity minus 0.
Exactly. Yeah. So we can just do this as limit as b goes to infinity, integral 0 to b, 1 dx. That, as Yuski said, that's x from 0 to b. And boy, it just kind of, I mean, that's just infinity, right? Because it's the b. There's not much going on there. I mean, there's a lot going on, but we can do it pretty straightforward. So because I got infinity, I would say this diverges. And it's not one of those p integrals, right? It's not 1 over x to the p for the integrand. So we have to actually think a little bit. What about this one? So, what do you think, Kevin? Yeah, yeah, solid. Yeah, it's the area. So this one up above, just really quick, this is the area under y equals 1. So it's an infinitely long rectangle. That's got infinite area. So thinking about these things in terms of areas can also be enlightening. This one, same kind of thing. You could do this the way Yuski did, where you could actually work the integral out and find 1/2 x squared and then take that limit. Or you could look at this and realize that if we find the area from 0 to b and let that area go out this way, that's going to become an infinite area. So this one also diverges. Is that cool with everybody?
Yeah.
Yeah. All right. So I'll draw a picture. You should be able to draw a picture, of course. Maybe we should have another quiz of the graphs. So, 1 minus 1. What do we think? Let's work it through a little bit. Right. Think of cumulative area. So I'm thinking about the area from 0 on up to B. So let's let B be this red marker. What's happening to the area as I move this far? It's increasing, right? Area is increasing, increasing. And do you remember, this was like one of the integrals I got very excited about, integral sine from 0 to pi. Does anybody remember how much area is in that little bump?
It was like 1. No, it was
Twice that much, but that's perfect. Yeah, that's good enough. It's a nice whole number. So the area there's actually 2 in that little bump if we were to crank it through. But then what happens to that as I move this way? Remember, we're accumulating.
becomes negative.
Yeah, it starts. Yeah, so it's starting to subtract, right?
Yeah.
0.
And then by the time I get to here, what is the Q? So this is like minus 2 in there.
Yeah.
And this is 2. This is minus 2, 2. And minus 2. So what is happening to this quantity as we move out this way? Let's kind of sketch it. So you're gonna slowly rise. Let's actually maybe do a little thing down here of the cumulative area. And in fact, it's just going to be a cosine at some point. You know, you take the antiderivative, it's minus cosine. We could work this all through. But let's try to think it. So it starts out with 0 right here, and then we start to accrue area, and it builds up until we get to 2. Does that look reasonable? Do you see how that, make sure you understand that graph. Yeah, that's the key thing.
Can you say that last bit again until it gets to 2?
So yeah, so we keep accruing, and like right here at this point, I've got half the area. If I just think about to the left, and so that's, that's 1 at that point. I've got half the area, but then I keep going, and I finally accrue up to 2 right at the end of that first bump.
I don't understand how it can be 2 on the y though. It's a sine
This is the
only.
cumulative area axis. So here I'm accumulating the area.
Oh.
Does that make sense?
Yeah.
You sure?
Yeah, that
Yeah. Okay, cool. So then as I move this way, I start subtracting, right? Because that becomes negative. Right about there, what's the cumulative area? Half of that, so 2 plus
1.
minus 1. Yeah, 1 is the cumulative
One is
area.
the-
Yep.
Yeah.
Yep. So right about there, the area is back to 1. And then what happens by the time I get to here? 0. Cool. And that's just going to repeat, right? The cumulative area. So at this point, I've got a net cumulative area of 0. And then it starts again. And I see this basically happening over and over again, roughly that. Just in terms of the cumulative area. Does that ever settle down?
No.
No. If it's settling down, when the cumulative area settles down like this might, what you would see is something like this. You'd have this total area thing here, and you'd start off with 0, maybe, yeah, always, I guess 0, and you'd see yourself leveling off. You'd see yourself approaching that final area. And the further out you go, the closer it gets, but it's settling down. This never settles. So this integral diverges. We can't say it's infinity. We can't really say it's infinity because we don't know what the answer would be. It's somewhere between 0 and 2, bouncing back and forth forever. So this one also diverges. Just an important thing to think about. You need that area to settle down as you move out this way.
So that would be like a non-diverging, not that, the one up to the right, the total error. That one.
This one here.
No, the red one.
The red. Yes.
Yeah.
This is what a convergent one would look like. Yes, sir. Yeah. Exactly.
I guess that would also be converging.
Yeah. This is a little. It depends. Remember, because we know that. That's a great question. We know that this, which looks like all those 1 over x to the p grabs, look about the same. And there's some that are above, and there's some that are below. And remember how some of these converged and some of these diverged. So like if this is p equals 1, does that make sense? If this is p equals 1, then it just turns into a natural log, and that's divergent. So all this stuff up here is divergent, but all the stuff below is convergent. So that's in other words when p is less than 1.
Right, that's right. I know.
P is bigger than 1, sorry. P is bigger, yeah, but I
don't think I have class.
there's some confusion today on the classes.
Wait,
we could,
it's
yes.
converging when p is greater than 1.
P converging when p is greater than 1, yes sir. Because that brings it down, the area dies off.
Yeah, no, that makes sense.
You actually get this asymptote, whereas with p greater than 1, it just keeps growing and growing and never settles down.
Okay, I see that.
Cool, awesome. All right, let's look at something we haven't done. We did a lot of this stuff with the p's, and I know that must have been like narcolepsy or some sort of sleeping pill to listen to me babble on about that through Zoom on a Friday.
Yeah.
So that must have been rough.
Huh. Was it not
You don't have to agree that hard.
Was it not
but-
rough for you also as teaching on
No, it's cool. I like it. It's cool. It's just like, oh yeah, talking about math. Anytime I'm chatting about math, I'm good. Even if I'm just telling my dog about it. Oh yeah. No.
Do you do that?
No. Let's do this one. So let's sketch it out. You always want to know what it is you're working with. What I'm asking you is find that area. Could you do that, please? I left my beverage in my office and my tea is steaming. I can't blame Alexander.
I wasn't even the last one.
No, you weren't. No, exactly. I can't blame you in any way. I can't blame anyone.
Any other day, it probably.
It might, that's why, yeah. Let me just go right back. You know, just before I go, just your first step is always going to be. There we go. I thought it was another unexpected visitor.
No. Well, maybe. I don't know.
Yeah, that's strange.
Or is it just gonna
Likely he would go all the way back to his office for a drink. I think he's probably just gonna get some water though.
Where is it?
Carol.
Oh.
108, right next to,
Yikes.
yeah,
Oh, yeah.
by Dr. Gray and
Yeah.
Casanova and all the other math people. He's anti-elevator though.
Oh, shit.
Very anti-elevator.
That's what it says. Goodness, damn.
Did you see him?
No, Jose took the elevator. Dr. T takes the stairs, so they don't see it. Dr. T left and we're trying to figure out if he went to his office or if he went to just go get something to drink. But he said he forgot his left his drink in the office. Well, that answers that.
Wait, did you think it was somebody else
No.
that you were coming in? Okay.
No.
Okay.
We thought we weren't sure if you said you were going all the way to your office.
Oh, God. Oh, okay.
Yeah.
Got it. You know, it's all recorded, so if you were talking shit about it, it's all right there.
So, but you'll see us being unproductive, that's for sure.
Is that what's gonna happen?
Let's just put that out there now.
Okay, okay. Yeah, maybe we can do it together. Where's that? Oh, it is.
He's recorded.
Alright. Don't worry, I never watch these recordings, so whatever you said is all private-ish. So I'm gonna keep this part because I'm not doing that yet. What's the antiderivative of e to the negative x? Beautiful.
Yeah.
Because we're using, of course, that, right? Because of course we use that, because you're looking at your sheets, I see that. You got your note sheets, you're doing that. 0 to b equals lim. B goes to infinity, now plug that shit in, so I got negative e to the negative b minus plus e to the 0. What is that?
Divergent.
Oh, I don't know about that.
Alright, then. Not-
So, what's a way I could rewrite this that makes it a little more obvious that it's not divergent? But I appreciate, just going for it. How could I rewrite this without the negative exponent? Could do this. First off, oh yeah, what's that?
1 over minus x.
Beautiful. And then this is just what's e to the 0?
1.
Thank you. What do we have here? We have something that's fixed over something that is blowing up. Where does this go? 0. Let's make sure we all see that. Does that make sense? Do you see? Again, I'm using that reasoning, using those words. The top is fixed, the bottom's blowing up. Atman, can I help you? I see your furrowed brow, my friend.
What is it? 0.
Why is it 0? So think about what E does. So just looking at that, look at that. What happens to that quantity as B gets bigger?
Oh.
You see that?
But E would get bigger, but since it's on bottom, that's why it's getting smaller.
Yeah, so the denominator is growing.
Right, which makes the whole number
Which,
get
and
smaller.
since the top is fixed, yeah, it's 1 over a billion, 1 over 10 billion, 1 over a trillion. Yeah, does that,
Yeah.
yeah. So this goes to 0. And so the area is beautiful. Yes, sir?
Can you explain that again? Why it goes to 0?
So if I have 1 over a large number, just in general, is that big or small quantity?
It's a small.
Small quantity. What happens is this gets bigger.
It gets smaller.
A bit smaller.
Yeah. Does that make sense? You understand just that part?
Yeah.
Okay. So here I've got 1 over, let's just look at it without the, what is happening to the bottom? What happens to e to the x as x gets bigger? So think about when x is 2, it's e squared, that's like 9. When it's 3, when x is 3, that's like 3 cubed, that's 27. So this quantity in the bottom gets bigger as x gets bigger, and you know this. You know that, Jose, because you know e looks like that. So as the x gets bigger, the output gets bigger. So I've got 1 over a thing that's growing bigger and bigger unboundedly. The whole ratio is shrinking. Or think about the graph of e to the negative x. That looks like this. And you have exponential decay as well. So you could look at it here and go, oh, there's e to the negative b. B is getting bigger, so this quantity is shrinking to 0. Even though there's a negative out in front, it doesn't matter, it's coming from the negative side. I don't know if I believe that.
No, I do get
Okay,
it.
okay, all right, all right, yeah, don't just humor me. Okay, all right, cool. So let's do another one. I'm trying to set you up so the web work is pretty easy. That's my goal. My goal is to have that happen.
Web work be easy, but not boring.
Yeah, I know. I saw you see space too. It's like, I know you have a. Yeah. I can read beyond. I can read. Let's look at a different kind together. No, let's do 1. X squared dx. Oh boy. Uh-oh.
What are you uh-ohing?
Double infinities.
I didn't even say uh-oh.
I'm That's my job, man. To foresee the excitement. Call it out as I see it. So let's look at that graph.
Yes.
Y equals 1 over 1 plus x squared. When x is 0, y is 1. What happens to y as I move out this way on the x-axis?
Y will decrease.
Decrease. Does that make sense? Again, fixed thing over a thing that's getting bigger. Yeah, and we can even, if you, and let's get a few points. I'm sorry, were you asking something?
Well, I was just gonna say, based off of, does that automatically tell you that it's a diverging graph, or do you have to do the integral bit first? To know that?
This graph is going to look like it's going to settle down. In fact, it's going to have an asymptote of the x-axis. So when we talk about divergent though, it's only in terms of the integral value, not the integrand.
Okay.
Yeah. So if you did this thing, it kind of looks like a beautiful bell curve. That. It's really nice. It's a great curve. It's like one of my favorite. That's a beautiful function. So this problem is saying, what's the area? Any suggestions on what we could do here to make this problem? How could we make this problem involve one infinity?
Split it at 0.
Oh, I like it. So what do you mean exactly?
So do it from negative p to 0, then from 0.
Love it. Yep, and in fact, that's the right answer. So when you have a doubly infinite integral, break it into 2. And think about the area, right? I want the area from minus infinity to here, plus here. Having these pictures and thinking geometrically is going to make you have some calculus superpowers, because you're going to be able to understand this more intuitively. And just make sure you do. Everybody cool on that? Athman, you cool?
Yeah.
Okay, cool. All right. Vincent, you cool on this? You're good? Okay, awesome. So, what do you think this area is compared to this one? What do you think this area is versus that area? Equal what? They look the same. How could we convince ourselves they're the same? I agree, they are the same.
Is it because they meet at the same y point?
Like right here? I could do stuff where this side is weird, goes through that, and then this side looks like that, right? So it's not just a point.
Because they're both going to infinity? Like one's going to negative infinity and the other one to infinity?
Yes, but what if I had this?
Yeah, right.
Going to infinity, but this area definitely looks different than this one, right? Because it's got subtraction. What were you saying?
I think, like, to the left, the function will be different from the one on the right.
This one here?
Yeah, I think the one to the left will look different from, like, the function as a whole will be different from the one that goes to the right. But this one is 1 over 1 plus x squared, and it's the same as, like, the 1 over 1 plus x squared.
Yeah, yes, absolutely, 100%. Do you know what algebra could I use to convince myself? What is the geometry term we're looking for?
Symmetry.
Oh, beautiful, yes. How do I know that is symmetric about the y-axis? So what test could I use? No derivatives, no calculus.
You didn't say it.
I knew where you'd go with it, I knew where you were going. Is that where you were going?
No.
That's right.
Okay,
That's
Vincent,
right.
what do you tell me?
It's like that one line test, you know,
That's what we.
like in, like, I don't know, high school or freshman year or whatever,
Yeah.
that one test.
Cool. So I know, so the test Vincent is thinking about is there's one that's the function. Is it a function, right?
Yeah.
So if I run a vertical line across and it ever touches more than 1 point, I don't have a function. This one, this horizontal line test is to test if your function is 1 to 1. In other words, this function is not 1 to 1, neither of these are, because there are two different x values that give you the same y value. So that's what that horizontal test would tell me. If I ever intersected more than one point, there's two x values that spit out the same y value. So I like that, but it's actually not that sophisticated. That's pretty sophisticated. But it can't tell us symmetry, because this thing passes, this would pass the same tests as those guys would, yeah? What else?
Some value of x.
Yeah, so, okay, now we're talking.
Yeah, so, I don't know what that would be, but some function.
So f is even functions that ring ancient bells, even if f of x is the same thing as f of negative x. That's the test. And even also means symmetric about the y-axis. Do you remember what odd is? Anybody remember? Yeah, let's start with here.
Wild take, f of x.
That's this guy, so that, yeah, in just different order. So yeah, there's good wild take, yeah, so we'll put that, that's actually part of it.
Plus one.
Is it f of x minus f negative x?
Yes, you can pull the minus out in front. Yes. So if this is odd, and this indicates symmetry about the origin. Now that's a weird one. What that means, symmetry about the origin means to get the graph to land back on itself, you flip it over the y-axis and then the x-axis. That is symmetric about the origin. So that's a weird symmetry. It's a hard one to imagine. I don't have a picture of it up here yet, but we'll see one very soon, actually, in just a second. So this function is even because it doesn't matter if I put positive or negative x in, I get the same y value out. Right? You put 3 in here, you get the same thing as you get when you put negative 3 in here. So it doesn't matter if I put in x or negative x, I get out the same y value. So that is the symmetry here. So that was a long way toward not even getting to the point I wanted to get to. So this is even. What does that say about this area versus this area?
Yeah, symmetric.
It is symmetric. So since it is symmetric, what is true about the two halves in terms of area?
They're the same.
They're the same, right? If this area on this side is different than this area, this thing can't be symmetric. It's got to look different on the other side. So this thing here, we could do what Kellen suggested, and that's actually the general perfect thing to do. But we could also realize that this is just twice half of the area. So I'm using geometry to make my life easier. And I turned it into something without two infinities in it. Do you see that? This is only because of symmetry that I can do this. Think about folding the two halves. They match up. Yes, sir?
So, would you also write that for the negative infinity to 0?
Wait, that's.
Yeah. Yeah. Well, yeah. So I could also say, or it's equal to 2 of this guys. Yeah, exactly. I think this is what you're saying. Yeah, that's right. Yeah. It's just that damn negative infinity is unpleasant. Nobody likes thinking about negative. What's this? Yeah, pick any of them. Yeah. So do this one if you want to do integrals twice. Go for it. Do one of these if you want to do integrals once. And do this one if negative infinity is not good on your brain. And it's probably not. So, quick little tip. If you ever need to take a limit at minus infinity, So if I told you, take the limit as x goes to minus infinity of some function. So this is just a note. You can just take the limit at positive infinity, but you replace the x with a minus x. They get you the same place. It's either the minus is happening before you plug in the x, or it's happening right as you plug in the x. So you could do that, just in case you ever need it. But we still need to get that integral, so let's do that integral. And you might need a table. I'm gonna actually ask you to look something up for me. So we got this, step one. We're gonna do two of those. Two, limit as b goes to infinity, integral 0 to b of 1 over 1 plus x squared dx. Can somebody, what is the antiderivative of 1 over 1 plus x squared? You might know it. It's actually like a not crazy one. You have to think trig. It's a trig derivative. So somebody can look it up for me or just know it, but I'm not freaking giving it. Let's see if you can find it by the time I scoot over there. So it's like a horrible video game. The worst video game you've ever played. It's like frog fractions, but terrible. Nothing yet, huh? You got nothing? I'll just meditate. Oh, thank you, God. Yes, thank you. That is the arctan. Arctangent, let's take a quick dive into arctan, because this function shows up more than you would think it would, and maybe more than you would like it to. So it's asymptotic, doubly so. That's pi over 2, that's minus pi over 2. You've got two horizontal asymptotes. And it looks like that. Now that is symmetric with respect to the origin. Flip it over, you get this guy. Flip it this way, it lands back on itself. So that's symmetry with respect to the origin. Hey, do me a favor, what's this? Limit as x goes to infinity of the arctan of x. What is that? You don't need to look, and no more looking up needed, just looking there. Pi over 2. What is the limit?
The opposite.
Yes.
Negative pi over
You see, you're reading my mind. That's how you do it. This guy, arctan of x equals minus pi over 2. Yay. Cool. Good stuff. So, back to our problem. This is that, is that, is this. Arctan of b, of x, excuse me, from 0 to b equals 2 lim b goes to infinity. Arctan of b. What is the arctan of 0?
arctan is 0.
0.
0. Awesome. Yeah, there's a graph, right? That's 0. So this is just twice the limit as b goes to infinity of arctan of b. This is 2 times what number?
Let's see, pi over 2.
Beautiful. So look at that. Pi is the area. Yay. So pretty.
Isn't that something?
It is cool. I think that's pretty lovely. Who would think pi would come out of that weird thing?
I mean, not at first, but now that I look at it, I can definitely understand
Awesome.
where you get like a trig thing.
Nice. Yes.
Why do you want to do like the two of the, you know, the limit of?
Oh, so here, what I was doing, use case, I was noting that the whole area is twice just half the area.
Yeah.
So it's twice the integral from 0 to infinity of that quantity. And then I just kind of followed through our process here. So this integral is just this without the 2, right? This is the definition, and the way you do this integral is you replace the infinity with a b.
Yeah.
And so that's what I did. Is that not what you're asking, or?
Well, it's more like, so this, the arctangent graph
Yes.
is negative, so I feel like when you did that like sine graph, it was like 0,
Yeah.
but this one is like, you have a number.
So we're not finding the area here.
Oh, you are?
No. This is like cumulative area. This is like the cumulative area graph. So this is, now I'm confused, let's see. No, I'm confused as to what I was telling you.
We were using the arctangent graph, I thought, just so we knew the values of infinity
Yes.
and 0.
Yeah, absolutely. So this is the area we're finding. It turns out its antiderivative
Oh, I see.
is just that graph there. Yeah.
Okay.
Does that help?
Yeah.
Okay, cool. Good. I think we're almost done. I got one more example for you, unless there's more questions about this. Just so that you don't lose your minds when you see it.
Is the 1/1 plus x squared like that function itself, the arctangent?
It is the derivative of arctangent.
That's what it's, yeah, sorry, that's what I meant to say.
Yeah, it is.
I just
yeah.
didn't,
Is that,
Yep.
that's what you're asking? Okay, cool. Last one.
if you have, sorry, I just gotta ask.
Yeah,
if
go
you have
for it.
like a 2 plus x squared or like something else on the bottom is the same thing, but different.
Yeah, it gets a little weirder. So when you have, what is the antiderivative of like a squared plus u squared du? I think if you look it up in the table, and somebody could tell me this if anybody in
I
this
was just
class
thinking
had a
of, like,
table,
Constant.
but I know we don't.
I got a table, it's right here.
Oh, cool, look at that.
Come on.
I'm just sorry, being such a smart ass, but I think it's that.
Oh, sure, so the arctangent still applies?
Yes, sir.
Okay.
Is this, did I get the formula right?
Oh, I didn't dive into it, I'll look for you, but.
Thank you, please look for me. Somebody freaking look at that table one time this semester, specifically now. Alexander will do it for us, so that's nice.
A lot of formulas through there, guys.
It should be on the first page.
The first page.
Yeah, don't keep digging. If it's not in like 1 through whatever on that first page of integrals. At least I think so.
Du over a squared, oh well,
Yeah. Do you over these?
Did you find it?
is it this one? It's not an arc sign or arc. This is a subtraction.
That's actually.
Here we go, right here.
There it
That's
is.
right there.
Okay, I got it.
Yeah,
Okay,
sorry.
cool. So which formula was that, by the way?
17.
That's formula 17. Awesome. Cool. Last one. We good? We good? Okay, awesome. Okay. So what would happen if I didn't have these on there? What would you do?
Integration by parts?
Oh, thank you.
Tabular.
Yes.
Tabular integration.
Yeah, we could tab this shit, but it's parts, yeah, perfect. Thank you. So this is gonna be the same, except we're gonna have to do a limit at infinity after we do all our work. So let's go ahead and just make this look less weird. And you're just putting the weirdness off till the end, that's all. X dx. So let's do this guy. So what is u gonna be?
X.
Awesome. Yep. Yeah, well, we already did that one, so I'll just give you that one there, yeah. And so then this is gonna become limit, carry that limit along. To remind yourself, I still have to do that. This is gonna be negative x e to the negative x from 0 to b. That's the uv. And then minus integral v to u becomes a plus because the minus on the v. stop. Make sure you're with me. And then, so, yeah, everybody's still writing, people still thinking, right? So let me know when it's cool to go on. Can I get, yeah? Just make sure you're following and you understand how I got there. It might take you a while longer, but if you can read this and know what happened, that's all that matters. All right. So now I'm going to plug in the B. Well, we already did this one, didn't we? We actually did. This was one of the first examples we looked at today, maybe the fourth example we looked at. Well, let's go ahead and do this part here first. So this is going to be minus b to the negative b minus, but look, this x is going to become 0, so I'm just going to have 0 there. Does that make sense?
Yeah.
Okay, cool, awesome, beautiful. And then this piece, we're just going to go ahead and do that. That is minus e to the minus x from 0 to b. Using this. K is -1.
Yes.
Yeah. Cool. We're good? Okay. So now I'm going to expand this out a little bit more. Limit as b goes to infinity of, I'm going to rewrite this as a fraction. Because this is in an indeterminate form, and we have to be really careful. Indeterminate form should always be done as a ratio. And what do I mean by indeterminate form? If you have 0 times infinity, that's not 0. We don't know what that is. That could be literally any number you want it to be. And I can prove that. If you want me to find a limit that looks like this that equals your favorite number, I'll do it for you. But if I have this, I have to convert it into a fraction. So you literally convert it into like 0 over 1 over infinity, so that the top is going to 0 and the bottom's going to 0, or you put the infinity on top and turn the bottom into a fraction, so that you have an infinity over infinity form. So the goal here is to make this thing L'Hopitalable. And now it's L'Hopitalable. So notice that I've got a fraction now. The top is going to infinity, and the bottom's going to infinity. So I can use L'Hopital's rule to take that limit now. And then this guy here, this is going to be minus e to the minus b. And notice that I'm going to subtract off e to the 0, but there was already a minus, so it becomes plus 1. So let me stop. Wow, honestly, I can't believe what this area is going to be. I'm shocked. This is kind of cool. This is a cool day for me because I didn't realize that this would also be 1. Yes, sir?
Why did you write +1?
Because I put in, when I did this part here, Jose, so let's just write that out separately. Put in the b, and this is 1, so this is, does that make sense? And then I was subtracting it, so it became a plus. Cool, that's good questions. Yeah. People worry about asking questions, like I'm so happy because that means you care. It's like, you're not just sitting here thinking about like whatever you're gonna eat when you get out of class, you know? That's great. So let's take a little bit of scratch work. What does this one do? What does this do as b goes to infinity? And maybe if I write it like this.
It gets really small.
Wait,
It goes,
0.
Yes. So it does get smaller, bottom gets bigger, top is fixed, goes to 0. We've seen this over and over again, right? Like this keeps happening. Is everybody cool on why that goes to 0? No? Cool. Alexander, you cool?
Yeah.
Yeah, cool. Vincent, you're cool. Okay. So now we've got 1, we've got 0. We just got to nail this shit down. So let's just take a look at it. We'll forget about the negative because we can always pop that onto whatever. So this is an infinity over infinity form. Top's going to infinity, bottom's going to infinity, a lot faster than the top. And that's gonna be why it turns out to be 0. Because the top is blowing up, but this is blowing up way, way, way faster. We're gonna see that this is 0. But the cool thing is it's L'Hopitalable, so I can use L'Hopital's rule. And the derivative of the top with respect to b is 1. The derivative of the bottom with respect to b is e to the b. And we just literally did that shit. What is that limit?
0.
That is 0. Yep. So this also goes to 0. And our answer is 1. That is the area. This is why I'm freaking out. Because it's so cool. This is a great day for me. I can't be like, seriously, like it's mathematically orgasmic to like realize this, that this area here is 1, and this area under e to the negative x is 1, right? We did this integral, and that was 1. But then this integral is 1. That's crazy. That's crazy. Wow. Who'd have thought? I wouldn't have. So thanks for being here while we saw that together. So now I got a new one, that lump of sine, that's got an area of 2. That was like my old favorite. This might be my new favorite right here. All right, guys, let's do some web work. I've done an example of every kind. If you don't have your laptop with you, which you may have been intentional, so you didn't have to do web work. I guess you get your phone out and like,
I'm too responsible.
yeah.
Maybe I'll just head out, I have pizza from the fridge.
Okay. Okay, that sounds good. We'll see you on Wednesday, which is our last day of the week. That's break weekend.
Do you have to
coming
come on
up.
Thursday? Do you come at all on Thursdays?
I teach online on Thursday. I do the prison stuff on
Right, I know,
Tuesdays
that's why I
and
wasn't
Thursdays.
sure if you came in.
Bye. I'll see you on Wednesday.
Here or not.
To the great dismay of my department chair.
So I have a question.
Yes, sir.
Why like is it one is b over e to the b equals 0?
So, where's the top going? Let's think about the fraction. We're sending b to, I think this is what you're asking.
Oh yeah, no, the other one.
Oh, I'm sorry. This one here?
The other one.
This one. Okay, that's what I was, so this is the scratch work down here.
Oh okay.
So,
The infinite. I got it.
you, okay, cool, awesome.
Yeah.
Thank you for caring. Always great,
Why
yes,
don't
sir.
you get rid of the negative?
Oh, because, so yeah, that's a good question. It turns out it doesn't matter, luckily. So I could have put it here. If I was copying things down directly, right? And then I would have just moved it out front anyway. And so we've just got -0, so it kind of washes away. Yeah, okay. There's one on there with a graph that'll be, I hope it's readable and that it's not too gross looking. Did you have more questions?
No,
Oh, okay.
I just,
You okay?
Huh?
You're okay?
Yeah.
Okay, cool. I'm just checking. All right. Okay.
I don't know, I'm just tired.
Understood.
I woke up earlier than I should have today.
You what?
I woke up earlier.
Oh, what's early?
Well, I mean, I usually, like on Mondays, Wednesdays and Fridays, I wake up at like 8 in the morning. But I woke up like around 6.
That's a lot earlier.
Yeah.
Yeah.
And then I saw like the light from the outside. And once I see light outside, I cannot go
You're
back to
done.
sleep.
You're up. up early today. I got up at 5:45 today. I'm not trying to outdo you, but I did. And it was miserable. But I was stressed about my first lecture today and I wasn't quite ready for it. So I had to get up and like,
We can just say it's a Monday.
what's that?
We can just say it's a Monday.
I think you nailed it on the head. Yeah, I should go like buy a tea or something. Yeah, I'm gonna go get a tea. Be right back. Anybody need anything? No? Get you a coffee if you want one. You guys good down there? Okay. Okay. You're so welcome.
Imagine the whole class was like,
I was a little worried.